Hello everyone. In this class, we will start with some basic background on random process, probability and random process that we will need in this course. So, it is most likely that this is already known to you, but nonetheless it will be used in this course. So, we will just revise the background that we will need. So, we will start from the basic definitions of related to probability and random process. First of all, in the basic framework there is an underlying experiment, maybe a practical experiment or some experiment that is performed by the nature, not by anyone. Okay. So, the experiment may be like tossing a coin or throwing a die, or it may simply be some electrons moving inside a register, and then the outcome there may be that some voltage observed at the ends of the register. In the case of throwing a die, the outcome is the number that comes on the face, and in the case of tossing a coin, the outcome is head or tail. So, there is an experiment and there is an outcome of the experiment. Now, the set of outcomes is called the sample space of the experiment. So, in the case of tossing a coin, the sample space is the set of head and tail. In the case of throwing a die, the sample space is the set of numbers from 1 to 6. In the case of the voltage at the output at the ends of the register, the noise voltage that the register is generating, the outcome is simply the voltage observed at the ends of the register. So, that voltage is continuous valued, it can be anything from minus infinity to infinity, whereas in the case of throwing a die, the outcome is bound to be from one of the 6 numbers, that is 1 to 6, and in the case of tossing a coin, the outcome is one of the 2, that is head and tail. Okay. So, the set of outcomes, that is the sample space, may be a finite set or an infinite set, it may be a discrete set, it may be a continuous set, it can be of different types. Okay. So, we know what is, so there is an experiment and there is an outcome of the experiment, and the sample space we will be denoting it by S, is a set of outcomes. For example, this may be the set of numbers from 1, 2, 3, 4, 5 and 6 when the experiment is throwing a die, or it may be the set head and tail. An event, so this is sample space, an event is simply a subset of S. In general, the definition is little more complicated, there are some conditions to be satisfied, but we will not go into the details, and we will simply will assume that these subsets that we consider are nice enough, and let us simply say that an event is a subset of the sample space. For any event A, there is of course the complementary event, that is A complement, which is set of all the set S minus the set A. Okay. Now, corresponding to an experiment, there is a sample space, but at the same time every if the sample space is finite, for example, every point in the sample space has a probability of coming as outcome. So, there is a probability measure associated with the sample space, associated with the experiment. The measure is on the sample space. So, for every event also there will be a probability, that is the probability that the outcome will be in that set, in the set A. So, that will be called the probability of the event. For example, we can take A to be the set of even numbers 2, 4, 6, that is a subset of this sample space. And if the die is fair, that is if the probability of each of these numbers is 1/6, same and equal to 1/6, then what is the probability of this event A? This is half. Probability that we will observe A, that is the outcome of the die will be throwing the die will be even number. So, that probability is in this case half. Okay. So, there is a probability of every element in the sample space in this case when the sample space is finite. Okay. Now, if we have some events A1, A2 and so on, some many events, then we can of course take the union of these events, then let us call it A, that is the union of all these events. And then what is A? It is basically the set of all numbers that are appearing in all these. So, the probability of A can be bounded by the summation of the probabilities. It may not be same as the sum of the probabilities, but it may be less than the sum of the probabilities. Why? Because there may be some common elements between the events. For example, we have taken one event like this, there may be another event we can take as A2 as 1, 2, 3, and there is this 2 is common. So, probability of this is half, probability of this event is also half, but the probability of this union this is not 1, it is not half plus half, because the probability is 1, 2, probability of 1, 2, 3, 4, 6. So, 5 by 6 is the probability of this union this, but it will be always less than equal to the sum of the probabilities. Now, if we have two experiments, say experiment 1 and experiment 2 with two sample spaces, say S1, which is this. For simplicity, we are considering now only sample spaces of finite size. Let us consider these two experiments with sample spaces S1 and S2. Then, if we take any one element from here and one element from here, what is the probability of that? That is, take xi from here and take yj from here. Then what is the probability that the outcome will be of the first experiment will be xi and the outcome of the second experiment will be yj? That is, we perform both the experiments, and what is the probability that the outcomes are xi and yj? So, this will be obviously in this range, and this is called the joint probability measure of these two outcomes. And once we know this joint probability distribution, this P, we can find out the probability distribution of this outcome, and that is called the. So, for that we have to take, say for example, if you want to compute the probability of xi. So, that is the probability that the first outcome is xi and the second outcome is any of these. So, second outcome can be y1, it can be y2, or it can be yn. So, we have to take sum of all such probabilities, that is probability that the first outcome is xi, but second outcome is y1, then probability that the first outcome is xi, but second outcome is y2, and so on, all those. So, we have to take the sum over all j, and this will be the probability of the first outcome being xi. So, if we know the joint probability distribution, we can find the individual probability distributions, and these are called the. So, if we want the distribution of this, then we have to take the summation over I instead. And this we get probability of yj. So, these two are called the marginals, marginal probability distributions. Marginal probability distributions. And again, let us consider that there are two events, either of the same experiment or two different experiments, and we know that one event has occurred. Then what is the probability that the second event is also occurs? So, for example, we throw one die and we know that the event of even number has occurred, that is the outcome is an even number. Then what is the probability that the outcome is 2? Then the probability is obviously 1/3 if the die is fair, because if we know that the event is even, that the outcome is even, then there are 3 such numbers with equal probability, each of them having probability, then 1/3. So, that to deal with that kind of situation, we need to define what is called as conditional probability. So, if there are two events, probability of this A and B, then if B is known to occur, B has occurred, then what is the probability that A is also true, that is A also occurs. So, that is defined as A B by probability of B. So, this is the marginal distribution, this is the probability that both A and B is true. So, these events may be of two different experiments or maybe the same experiment. Okay. Similarly, probability that B given A is probability A B by probability of A, and from these two one can see that from here we can write probability of A B is probability of B times probability of A given B. So, this is quite expected, because what is this? This is the probability that both A and B are true, both the events A and B occur. Then that is same as the probability that B occurs, and then given that B occurs, what is the probability that A also occurs. So, if you multiply those two probabilities, that is what is the probability that B will occur, and then what is the probability that if B occurs, what is the probability that A will also occur. So, those two probabilities together will give you the probability that A and B both occur. Okay. So, this is also called chain rule of probability. So, we will see a generalization of that. The generalization is, if you have now T events A1, A2, AT, one can show that this probability is probability of A1 times probability of A2 given A1, probability that A3 given A2 A1, probability of A4 given A3 A2 A1, and so on till probability of AT given AT minus 1, AT minus 2, and so on till A1. This can be written in short as probability AI given AI minus 1 to A1. So, this is called chain rule. And now from here one can say that one can now express, suppose we know that we know this probability, but we want to compute this probability. So, what is the way to compute B given A, probability of B given A from probability of A given B? So, in this expression this does not appear, but then this one can be expressed in terms of this. Here is how it can be expressed in terms of this. So, we can write probability B given A as probability of A B, that is this probability of B times probability of A given B by probability of A. Okay. Now, if two events are there A and B, they are called independent if this probability is same as, so A and B are called independent events if PB given A is PB. That is, B given A, whether A has occurred or not, it does not matter. To compute the probability of B, whether A has occurred or not, it does not matter. So, because B is independent of A, that is why it is defined this way. Okay. So, if we simply put this quantity equal to PB, what do we get? This PB cancels from both sides, and then we get PA given B equal to PA. So, that is equivalent. Now, on the other hand, if we put here this equal to PB, what do we get? We get PAB equal to PA times PB. So, we get, this is same as saying that PAB is PA times PB, that is the probability of A and B together is equal to probability of A times probability of B. So, this is also same as saying P A given B is PA. So, these are all same, equivalent, and if this is true, then these two events A and B are called independent events. Okay. Now, we have a sample space S corresponding to an experiment, and if we consider a mapping X of S into R, that is, what is this mapping? This takes every element from the sample space to a real number. So, the outcome of the experiment may not be a real number. For example, the tossing a coin, the outcome is either head or tail, it is not a real number. So, but we can associate with every outcome a real number, so that for every experiment the outcome is mapped to the set of real numbers. The mapping can be in different ways, but we can map to the set of real numbers, and such a mapping is called a random variable. So, there is an experiment and there is a mapping of the set of outcomes to the set of real numbers, and that mapping is called the called a random variable. So, if we have a random variable like this, so this is a random variable. For let us see some examples. So, consider coin toss. So, S is head and tail. Now, we can consider a mapping like this, where head is mapped to 1 and tail is mapped to -1, or tail is mapped to 0. That will be a different random variable. So, if we can take different mappings and there will be different random variables. Okay. So, this is an example of a random variable. Now, if the outcome, if the image of this mapping is a discrete set, okay, it is not continuous valued, then so if image of x is discrete set, then x is called a discrete random variable. So, x is called a discrete random variable. For example, in this case it is a discrete random variable, the mapping, because the image of the mapping is 1 minus 1. It has only 2 elements and this is a discrete set. On the other hand, if we take the voltage across a resistor, the noise voltage, that thermal noise that is generated at a resistor, it is continuous valued. That is also a random variable. The outcome itself is a real number, and the mapping can be taken as just the real number itself, the identity mapping. So, every real number goes to itself, that is the mapping. Then that is the image of the random variable, the mapping, is a continuous set. It can be anything. It is not either +1, -1 or +2, 0, it is not integer, but it can be anything. So, it is a continuous random variable. So, if the image is a continuous set, then x is called a continuous random variable. Okay. Now, let us define some more probabilistic functions and concepts regarding random variable. So, the random variable, the values taken by random variable are real numbers, unlike the outcome of an experiment, which may not be a real number, like the head and tail for coin toss, they are not real numbers, but the random variable is defined in such a way that the value is a real number. So, we can now talk about what is called a probability distribution, or also known as cumulative distribution function. So, it is basically for any x, take any x which is a real number. So, we denote the set of real numbers by this symbol, that is the real line. Then take any real number x which belongs to this set. Then the probability distribution function of the random variable capital X. So, we have a random variable capital X. So, for that random variable, this function f x is defined in the following way. What is f x at x? X is small x denotes a value, a real number. So, whereas this capital X is the random variable, the mapping. So, capital X, this f x at x is basically the probability that capital X is less than equal to small x. So, that is, if you take a value small x, what is the value of this function at small x? The value is the probability that the random variable capital X will be less than small x, less than this. The probability that the value of the random variable will be on the left side of small x. So, that is that probability is the value of the function at x. So, obviously, that is less than 1, but greater than 0. It is between 0 and 1 because it is a probability, and also it is increasing as x increases, because if we take 1 x equal to 1, the value is the probability that the random variable is less than 1. Now, if you take the value 2, the value of the function at 2 is the probability that the random variable is less than 2, which will be more than the value at 1. So, it is increasing as x increases. So, this is increasing or rather non decreasing, it does not decrease. So, it is non decreasing function. Let us see some example. So, we just now considered this random variable head tail mapped to 1 and minus 1. Now, if let us consider a fair coin where the probability of head and tail are same, that is half, then let us plot the cumulative distribution function for this random variable. So, this is 0. Let us consider say minus 2. So, at minus 2, what is the value? What is the value is the probability that the value of the random variable is value of this random variable is less than minus 2, but the value of this random variable cannot be less than minus 2 because it takes either 1 or minus 1 values. So, the probability is 0 at minus 2. So, for any value less than minus 1, the value any real number less than minus 1, the value of the distribution function will be 0. So, it is 0 here. So, it is the value is 0 here, and at minus 1, what is the value? It is still 0 because the probability that it is less than equal to minus 1. Now, suddenly here the value becomes half, because the probability that the random variable is less than equal to minus 1 is half. It is equal to minus 1 with probability half. So, the value is half here. So, this is half. And then probability that here the value is on the left hand side of this is also half, because it takes value only this, so these values are not taken, and this probability is half. So, it is still half, it does not increase, it is still half, and it increases again at 1 because this is the next value that the random variable takes. And here at 1, what is the value? It is the probability that the random variable is less than equal to 1, and that is 1. The probability is 1 because it is always less than equal to 1. The value of this random variable is always less than equal to 1. So, it jumps to 1 here. So, this value is 1, and then it remains at 1. It cannot increase more than 1, of course, because the probability cannot be more than 1. So, this is the cumulative distribution function of that random variable. Now, if you consider this is example 1 for coin toss, and Second example, if we throw a die, S is 1, 2 to 6, and each has, so it is a fair die, so each has probability 1/6. Now, so what is the cumulative distribution function of this random variable? Let us take 1, 2, 3, 4, 5, 6. So, if you take a number below 1, the random variable cannot be less than that. So, the probability is 0 everywhere here, the probability is 0, and at 1 the value is 1/6. So, it rises to 1/6, and then at 2 it rises to 2/6, then at 3 it rises to 3/6, 4/6, 5/6 and to 1. So, this is 1, this is 5/6, this is 4/6. So, this is the cumulative distribution function of this random variable. Okay. Now, for a continuous random variable, it will not, a cumulative distribution function will not look like this kind of staircase, because in that case there is the probability that the random variable takes a particular value will be 0. Because there are infinite number of values it can take. Okay. So, usually it will, whereas here there are finite number of points where it takes values, there will be infinite number of points between any range, between 0 to 1 itself may be infinite number of values, all the values can be taken. So, if they are all more than zeros, then the total probability will be more than 1. So, it is it rises continuously instead of like this. So, for continuous random variable, a typical cumulative distribution function looks like, may look like this. So, the maximum value is of course 1, the minimum value is 0. So, for any cumulative distribution function, of course, at x tends to infinity, that it will go to 1, and at x tends to minus infinity, the value will go to 0. Okay. So, for a continuous random variable, it rises smoothly, and if the derivative exists, then that derivative is called the probability density function. So, if we define another quantity, probability density function. It is basically, it is denoted by this, and it is d f x by dx. So, for this kind of cumulative distribution function, if you plot the derivative of this function, it will look something like this. Okay. And from this definition, one can see that this means f x is nothing but the integral of this. So, we need to take an auxiliary variable to integrate dy from minus infinity to x. So, this is basically the area under this curve till x. So, if you are this value is nothing but take this value here, this area. This area is the probability that the random variable's value is less than this, and that is same as this value, that is what is the cumulative distribution function. So, if we know the cumulative distribution function, the way to get the probability density function is to differentiate it. If we know the density function, we can get the probability distribution function by taking the integral minus infinity to x. Plot that as a function of x, we will get the cumulative distribution function. Now, if we know the density function, then can we compute probability of this type, probability that the random variable is between two values? Suppose we want to find out what is the probability that say we have the density function, say like this, and we have taken x1 and we have taken x2. What is the probability that the random variable will be in this range? The value will be in this range. That is the area under this curve from x1 to x2, because this is the density, this is really the density of the curve, that is density of the probability. That is why it is probability density function. The probability that the value is in this range is simply the area under this area. So, this is integral x1 to x2 p x y dy. Okay. And we can of course write this in terms of the cumulative distribution function also. This area is nothing but the area till x2 minus the area till x1. So, area till x2 is f x x2 minus infinity to x2, that area is this value, this value. So, this value is the area from minus infinity to x2 in this curve, and this value is the area from minus infinity to x1 here. So, if we subtract that, we will get this area, extra area, that is this minus this. So, this minus f x x1. Okay. Now, let us see some. So, we will just summarize by saying that this is a cumulative distribution function. This can be defined for any random variable, whereas the probability density function is defined only for continuous random variable. Let us see some examples of continuous random variable density function of continuous random variables. Uniform density function. The density function can be like this, say it starts from somewhere and say the width is say L, and then this value will be 1 by L, because the area under this curve, total area must be 1, the total probability is 1. So, this is this basically says that this is uniform, the probability is distributed uniformly in these two ranges, in this range A to B. And what will be the cumulative distribution function for this random variable? The cumulative, this is P x. What will be f x for this? Take A, B, it will rise linearly. So, this value is 1, and slope of this is basically this value, 1 by L is the slope of this curve. this line. The derivative of this is this. So, okay. Now, let us take another example which is very important in this course, Gaussian random variable. For Gaussian random variable, the density function is 1 by root over 2 pi sigma e to the power minus x minus mu whole square by 2 sigma square. Mu and sigma are two variables. Mu is basically what we will define later as mean, that is the center of the density function. So, suppose this is mu and take some sigma to be something, some real number, then some positive real number. Then this will look like this. This is going to 0, but it is never touching 0 actually. So, it is maximum at mu and symmetric around mu also. So, this is the probability density function. It is a bell shaped, famous bell shaped curve, and if you plot the integral from minus infinity to x as function of x, what will you get? It will be like this. The slope is maximum here, because this value is maximum. This is the slope of this curve. So, this is f x of x. There is no closed form expression for this. This is the integral of this from minus infinity to x. Okay. Now, let us consider multiple random variables. Suppose we have multiple random variables, just like we considered two experiments and consider joint probability, we can now define joint distribution. Say we have x1 and x2 are random variables, and then we can define f x1 x2, the joint cumulative distribution function, as it is a two dimensional function. Now, we take two variables x1 and x2, and this is the probability that x1 is less than small x1, less than equal to small x1, and x2 is less than equal to small x2. So, this is a function of two variables. So, to plot it, you need 3 dimensions, 2 dimensions for the variables and 1 dimension for the value. So, we can now differentiate it with respect to these two variables and get the density function p x1 x2 at x1 x2. This is del square del x1 del x2 f x1 x2 x1 x2, the derivative of this. Okay. And then we can write this in terms of this also, simply as integral. It is basically minus infinity to x1 minus infinity to x2, then p, let us call these two get some auxiliary variables dy1 dy2, the integral. From this density function, we can get the marginal density function of these two random variables separately. For x1 there is a density function, for x2 also there is a density function if they are continuous random variables. Then this density function is the joint density function of the two random variables. If we know the joint density function of the two random variables, this gives us all the information not only about two random variables, but obviously we can extract any individual information about any of the random variables, like the probability density function of the two random variables separately. That is the marginal density functions. So the way to get them is as, so the marginal densities can be obtained as Px2 of x2. This is the marginal density function of x2. This is minus infinity to infinity P x1 x2 and this is x1 x2 dx1. With respect to x1, if you integrate, then you get the marginal distribution of marginal density function of x2. Similarly, you can get marginal density function of x1 by integrating the joint density function with respect to x2. Okay. So, we have multiple random variables, we have a joint cumulative distribution function and a joint density function, and from the joint density function we can get the marginal density functions by integrating with respect to the other variable. We can define just like for events, we can define for random variables, we can define conditional probability distribution, conditional density function and all those related quantities. So, the conditional probability distribution if you take x1 given x2, so x1 given x2, that is, if we know that the value of x2 is small x2, then what is the cumulative distribution function? Conditional cumulative distribution function of x1. So, that is defined to be x1, what is the probability of x1 less than x1 given that x2 is x2. So, this can be shown to be minus infinity to infinity x1, the integral joint density function this. One can show that this is same as this. Now, from here one can get conditional density function at x1 given x2. This will be simply del f x given x2 by del x at x equal to x1, and this is nothing but p x1 x2 at x1 x2 by p x2. So, this is just like conditional probability of two events, one event given the other. This is the joint. Previously we had the joint probability and divided by the probability of this. So, here also similar quantity, but these are not random variables, these are density functions of random variables. Okay. And so, from here we have chain rule that p x1 x2 is p x2 x2 times p x1 given x2 x1 given x2. If we have more random variables, we can generalize this just like we did before. And if now this is same as p x1 for all x2 and x1, then x1 and x2 are called independent random variables. So, independent if when are few random variables called independent, if we have these random variables, then they are called independent random variables if their cumulative distribution function factors this cumulative distribution function is the product of the marginal cumulative distribution functions. So, this is this times f x 2 times f x n. So, all the random variables are actually independent. The value of one random variable does not get influenced, the probability of x 1 being something is not influenced by what happens to the other random variables. It is basically that. So, this is true, and at the same time if this is true, one can also show that this x 1 this density function is also can be factored. So, these are x 1, x 2, x n. So, x 1, p x 2, x 2, p x n, x n. So, we have in this class we have discussed what is an experiment, what is an outcome of an experiment, and then we define the sample space to be the set of outcomes of an experiment, and then we define independent events, the conditional probability of one event given that the another event has occurred, and then we defined random variable to be a mapping of the sample space into the set of real numbers. And since the sample space has a probability associated because of the experiment, the random variable, the value of the random variable also has some probability measure on the values. So, using that probability we defined what is called the probability distribution function or cumulative distribution function. And then for a continuous random variable, that cumulative distribution function is differentiable and the derivative is called the density function. And we have actually seen why it is called density function. By integrating the density function in one range, you actually get the probability that the random variable will be in that range. So, it makes sense to call it the density function. And then we define joint cumulative distribution function, joint probability density function of some random variables, multiple random variables, and we define conditional probability distribution and conditional density function, and then at the end we have defined independent random variables. We will continue our discussion on probability and random variables in the next class also. Thank you.